DOE CSGF Fellow Harshal Kamdar in the field of computational astrophysics at Harvard University.
Hi everyone, my name is Harshal, and today I'm going to be telling you about some of the work that we've been doing for the past couple of years. In particular, I'm going to be talking about our galaxy, the Milky Way, and the study of something called Galactic Archaeology, which is a subfield that I work in. I'm also going to be talking about some of the models that we've built to study and interpret some of the data that we have on the Milky Way today. I'll start with a very simple movie that sort of zooms in and out of our galaxy. And this is an artist's illustration of what it would look like. But the point here really is that there's a lot of complicated structure going on, right? Like previously you saw the spiral arms, now you can see kind of the dust lanes and some gas clouds, a lot of stars, some clustered, some not. And as you zoom in to the sun, there's just a lot. It just tells you that there's a lot of vast scales involved in the evolution and history of our galaxy. And recently there's just really been a huge revolution in the study of our galaxy, and that's because of something called Gaia. So before 2018, we had the positions and velocities of about 100,000 stars in our sort of immediate neighborhood in the galaxy. But after one day in April 2018, we sort of have now 1 billion stars that we have positions and velocities for, which is just an absurd number, right? So essentially overnight, we have now more than 4 orders of magnitude more data volume, which is, there's a lot of information out there sort of waiting to be discovered. And these positions and velocities are sort of extrinsic properties of stars. Astronomers are also interested in intrinsic properties like the chemical composition of stars. So there's also been a bit of a boom in the data for these chemical studies. So before 2015, we had chemistry for about 1,000 stars precisely. And then in 2018, we've sort of hit 100,000 stars. And this is a bit outdated. Today, we have more like 100,000 stars, more like 1 million stars with sort of a lot of different chemical elemental makeup of stars. So there's just a lot of both chemical data and also phase space, so like spatial and kinematic data out there for stars today. And the subfield that I work in, the questions that it likes to ask are predicated on a very simple axiom, right? So it just says that the position, the velocity, and the chemical makeup of stars today holds valuable clues about the history and the assembly of our galaxy, much like archaeology and the study of human history. The 2 key questions here that we are after is, what is the history of star formation in our galaxy, right? Like, where were they born? When were they born? How many were born? How were they born? And then the second question is, how did the galaxy actually assemble over time? And what were the different large scale features that mattered in its evolution? And what can we learn about other galaxies by studying our own in so much detail? Right, so this is sort of a visual illustration of what I was trying to convey in the earlier slide. And it just shows a couple of just one movie of ink dissolving in water in 2 different mediums, in cold water and hot water. The point I want to get across is that stars born together are much like ink dissolving in water. Stars that are born together, they kind of move through the galaxy and dissolve in the galaxy as they encounter spiral arms and like molecular clouds and a lot of the violent features of our galaxy. So the point of this movie is that if you're able to somehow, and I'll play it again, you're able to somehow quantify in detail the visibility timescale of the ink, you're able to say something about the water. Similarly, you can do the same with stars and our galaxy, right? So if you're able to say something about how long stars are visible, you can say something about the galaxy itself and the evolution of our galaxy. Since there are not a lot of astronomers listening, probably, I'm going to make a bold claim. and say that there's really no current model that can that is able to probe the scales that are required to study clustered star formation. And yeah, I mean, the reason is that these cosmological simulations with hydrodynamics and isolated n-body simulations, they've been wildly successful in studying the bulk properties of galaxies and large-scale structure. The problem, however, is that the highest resolution in current simulations is, for these types of simulations, is about 500 to 1,000 times the mass of the sun. So that's one particle in these simulations. But the average mass of a full star cluster born in the Milky Way today is 500 times the mass of the sun, right? So this is just not a regime that is really being probed by these simulations yet. So that's what we spent a bulk of my PhD sort of building from the ground up. We sort of built an analytic model and semi-empirical model for the Milky Way. And this on the right is basically sort of the analog movie of ink dissolving in water, but stars born together dissolving in the galactic disk. And the colors are, they're sort of color-coded by what cluster they were born in. The key sort of properties of our model, one of the key things is that it essentially has a solar mass resolution. Each particle in the simulation is an individual star, which is something that is totally unique. To do that, though, we have to make a few concessions. So we have an analytical prescription for the life cycle of how star clusters are born and how they evolve and how they die. We have an analytical prescription for the potential of the galaxy. It's time varying, it's realistic, but it's still fundamentally analytical to make our calculations tractable computationally. We have a realistic error model because we want to go ahead and directly compare to the data. And we have a few control simulations that we are able to run just because our simulations take a few days to run on a supercomputer versus a few months for the largest and the best cosmological zoom-in simulations that I mentioned earlier. So after running these simulations, you can do a lot of fancy statistics. For the purposes of this talk, I'm going to focus on something very simple, and that's something called co-moving pairs. These are essentially a pair of stars that are very close together in space, and they're moving at a very similar velocity through space, through our galaxy. So these are essentially on a very similar orbit and are also spatially very close. And these are some papers that I've focused on co-moving pairs recently. Right, so the first and the simplest question you can ask is, how many are there? Like, as a function of things you care about, how many co-moving pairs actually are there in the data and in the simulations? So first I show here, as a function of the velocity difference, the 3D velocity difference of a pair of stars, what is the fraction of co-moving pairs within that velocity difference? And the white line is the data. And the dashed blue line is the fiducial simulation that we presented with everything, right? So it has spiral arms, it has the bar, it has molecular clouds. It's sort of all the ingredients together. And, you know, it agrees pretty well, but there's still a few key discrepancies at lower velocity difference. Then we ran a simulation without any perturbations. So we removed the spiral arms, we removed the molecular clouds. And just right off the bat, you can see that there's too many pairs, right? So there's no perturbations that are really sort of driving these pairs apart. And just by that very simple change, you get too many pairs. And then we also ran a simulation without clustered star formation. So instead of forming stars together in a cluster, just kind of put them in space by itself. And just right off the bat, you can again see that there's too few pairs in this situation. You know, this is a very sort of, these are extreme versions, but you can imagine like running like 1,000 of these simulations and slowly MCMCing your way to the real Milky Way and put sort of key constraints on both how star formation works and also how the potential of the Milky Way is, right? Like how many perturbers are there? How many clouds are there? How strong are the spiral arms? So these pair counts at small velocity separations are really sensitive to both of those things. Right. So the next question you can ask is, what fraction of these pairs were actually born together, right? Because I mean, the galactic disk has, I think, 45 billion stars. So this is a lot of 45 billion. There's just a lot of stars. So there's also a lot of chance for sort of random field alignments that of stars that are not actually born together. So here I show, as a function of the separation of pairs in space and the 3D velocity difference, so how similar their orbits are, what is the co-natal fraction? In each bin, what is the percentage of pairs in that bin that were actually born together? And red is 100%, and blue is 0%, and like white is like 50%. And you can see, like, for the smallest separations and the smallest velocity differences, you get the highest co-natal fraction, which is kind of what you'd expect. And as I sort of promised in the title of my talk, this plot right now is without adding any chemistry information, right? So this is only positions and velocities. So that little funky delta Fe over H on the top right is just the amount of iron that is in both stars, the difference in the amount of iron that is in both stars. Now, just if you measure the iron in two stars and you fold that information in, this is what you get, right? So it just kind of balloons out, and that's exactly what you want, right? So with just one extra piece of small information, chemistry, you are able to essentially get stars that were born together much further out in both both in real space and also velocity space. So that's pretty cool. And the point here is that if you combine kinematics and chemistry, you can essentially recover more stars that were born together in the disk and do these comparisons and studies in more detail. The future is really bright for galactic archaeology, in my very biased opinion. There's a lot of data coming in the next 10 to 15 years. This is the footprint for an upcoming survey that will measure the chemistry for 10 million stars. That's 10 times the number of stars we have today. And then there's also going to be 10 times more stars with really accurate and precise positions and velocities coming in the next 5 to 10 years. So there's even more data coming, and there's a lot more discoveries to be made. And sort of our hope is that our simulations can play a small part in that. This is my favorite part of the fourth year fellow talks. It really takes a village to get here. So I want to first acknowledge the research group that I'm a part of at Harvard. I mean, I've just learned a lot from these people. This is the only photo I could find. This is from a hack week that we did in my first year of graduate school. But yeah, just a huge shout out to all of them. I've learned a lot from them, and especially my advisor, Charlie Conroy. I also really want to thank Dr. Caleb Phillips, who was my practicum advisor, and NREL for being such a welcoming host. In particular, I want to give a shout out to Dr. Stephen Hammond, who was the practicum coordinator, I think, the year I was applying for practicums, and Dr. Michael Martin. And finally, I also want to really thank everybody at Krell. The number of emails I've sent Lindsay over the years, it's kind of absurd, but this is such a great community to be a part of. And I hope I can continue sort of being a part of this community after I'm done with the fellowship. Yeah, thank you so much, and I can take questions.